Okay, hopefully the microphone is working with this. Let's see what's happening with it. Okay, hopefully the microphone is working with this. Let's see what's happening with it. Sorry for the echo. That apparently everything is working. I'm having some Zoom issues, and I apologize for that. All right, this is the recording after the fact of lecture 1 from earlier today. Sorry we didn't get to live stream it. I am Dr. Lewis Baum-Stark. I'm the lead instructor for CS 1301 this semester. And just a recap of what I do in the course is, first of all, I deliver this Monday lecture every week. I will also be developing all the homeworks and project assignments and things, as well as the exams for the course. And your section instructors for the workshops will be doing all the grading, running the workshop, and I'll be working with them to facilitate that. My office is TLC 2215. My email is lewisb@westga.edu. I'm also the CS and comp programs coordinator. I do some gaming, if you're into that. I also build robots in my spare time. Nothing fancy, just stuff to play around with on our local robotics competitions. All right. A reminder, if you're watching this on Monday or Tuesday, or even later this week, you do have to purchase the required Zybook and do so as soon as possible. I have moved the readings and activities that were should have been due by this lecture. I moved those to Friday of this week so you can get them done. Workshops still will meet this week, and they are required. Also expect a homework to be assigned on Thursday, due the following Thursday. Keep an eye on Moodle for those to appear. All right, we are going to get started in Java today and talk about variables and expressions. And as I told the live class, I expect that you have not ever had any programming. Some of you will have taken CS 1300 and have some Python programming there. That's great. Some of you have taken programming in high school, and that's great too. But I have to assume that everyone in this course has taken it. So we're starting with the very, very basics. An example to kind of set the mood, let's look at your equation for a line, which hopefully you've had in in math class some point in the past. If you haven't, you weren't paying attention in math class in the past. So here's their equation for a line: y equals m times x plus b, where x is the x coordinate, of course, m is the slope of the line in rise over run, b is the y-intercept, in other words, where it crosses the y-axis, and then y is the y-coordinate we're going to find. So for every unique x, there is a unique y that goes along with it. And this is the formula for determining y given x. Now, we have 4 unknowns in our formula. Y, which is what we're trying to find, m the slope, b the intercept, and x the x value we have. Let's go ahead and declare those as variables, meaning these are things we want to be able to hold and store a value. In all these cases, I'm going to call them, type them as ints. So I'm declaring y to be of type int, declaring m to be of type int, x to be of type int, and b to be of type int. A declaration tells us that a variable exists and tells it what kind of data is going to be contained in that variable. So Java is a little different from Python. For those of you who've had Python, Python just you assign a value to a variable and it figures out what its type is. And that's cool. It can, it's useful from time to time. Java is not like that. Java is a statically typed language, and we must explicitly tell Java what kind of data or the type of a variable. And we have to do that before we use a variable, which is why I have my declarations here. And then I go ahead and start calculating my formula. So which is right there, y equals m times x plus b. System, and then I'm using system.out.println to print this to the console. Now, the way in the previous slide, we hadn't actually given any values to those variables. Because of that, our program would, at best, would have undefined behavior, and it might not have run at all. So here, I'm giving values to m, x, and b, and I'm doing that with an assignment. Now, this equals means assignment. It means m gets the value of 3, x gets the value of 5, b gets the value of 1. Sometimes we can say that in reverse and saying 3 is assigned to m, 5 is assigned to x, 1 is assigned to b. This is not an equality. This is taking the thing that's on the right side and smushing it into the box that's on the left side. So after m equals 3 executes, we know that the value contained in the variable m will be 3. Now then, when we get to our y equals m times x plus b, we actually have values we can substitute for each of these variables. M will be 3, x will be 5, so we multiply those together, we get 15, plus 1 for our b gives us 16. That's what will get assigned into y. So we can also take the resultant expression and assign it into a variable. Now with this slide, we're kind of combining the previous things. We're taking our declarations and our assignments and putting them into a single step. And this is okay. So here, we did our declarations first and then our assignments. But there's no reason we have to do that. And in fact, sometimes it looks a lot better to do this. So here we're doing a declaration and assigning a value to it at the same time, declaring our variable m and immediately saying that m contains 3. Did the same with x, same with b. And then here we did it with y, only instead of having a constant on the right, we have our expression. All this is valid, and notice how much cleaner this looks compared to the previous slides. Our only rule here is that a variable must be declared before it is used. All right, now this program right here is useless. I mean, it's almost less than useless, because all it does is it tells us what y is when m is 3, x is 5, b is 1, because we've hard-coded those values in. No matter how many times we run this program, we're always going to get exactly the same answer. There's no way to vary the data in our variables. We've given them hard-coded values, and that's not particularly interesting unless we just one day think, I wonder what y I'm going to get if my m is 3, my x is 5, and my b is 1. That's all this will tell us. Instead, let's write a program that can actually take input. So for whatever value m is, whatever value x is, and whatever value b is, we can calculate our y. And that's what's going to happen here. This looks like some stuff you will read in the book at this point. This line, don't worry too much about what it is. All this does is it sets up a variable named keyboard that we're going to use to get input from the keyboard. Then we're going to do a prompt to the user, say, okay, enter the slope. And we're going to ask the keyboard for the slope by this next int. So it's going to assume we type in a number at the keyboard, a number without a decimal point, and it's going to convert that into an integer and assign it into m. Then we're going to prompt the user for the x coordinate, and then ask the keyboard for another integer, which will get assigned into x. Then we're going to prompt the user for yet another integer, for the y-intercept, get an integer from the keyboard. So it'll wait until the user types something in. And once that happens, we'll assign it into b. And now we can calculate our y value based on whatever values the user typed in when they ran the program. So much more interesting than what we had before, because now we have a program that works for any valid values we type in. and we don't have to recompile it every time we want to change the numbers. All right, I'm going to take a tangent for a second and talk about something called incremental development. Notice how in the previous slides we built up our program just a little bit at a time. In fact, at one point, our program was just these hard-coded values. And then later we added on the ability to prompt the user for these values. We call this idea of working on a piece of it at a time incremental development. We often call this code a little, test a little. We don't write the whole program at once. Instead, we write a small portion of our program. We test that thoroughly to make sure it works. Once that little piece of our program passes all our tests, then we add a little bit more code to our program and we test that. Then we add a little more to our program and test that. And in doing so, we build up a program that's not just thoroughly tested, but individual pieces of it are tested. And we have confidence that the whole thing works. This is far superior and in fact takes less time ultimately than if we write the entire program and then start the testing process. Okay, so back to variables. Just to recap, a variable is a name for a location in memory to hold a data value. These data members are variables. We talk about memory. Those of you who have built a computer, those of you who have spec'd out a computer, those of you who just know stuff about the hardware of computers, memory is RAM. All those, when you talk about your machine having 16 gigabytes of RAM or 32 gigabytes of RAM or whatever, that's really what we're talking about here. Memory stores variables as binary data, among other things. It holds other things too, but all the variables we declare ultimately get stored in RAM as our program is running. In terms of how we think about it, though, think of it as a big piece of paper. And every time we declare a variable, we draw a box on that piece of paper, and we put a name on it. And that name is whatever we name the variable. And then as our program executes, it reads and or writes values into those boxes and uses those as places to store its data as it runs. And when we declare a variable, it is always a type followed by a variable name. So we have three examples here. Int numapples, where int is the type, numapples is the name. String some text, where string is the type and some text is the name. And double price, where double is the type and price is the name of the variable. And on this slide, we have kind of a summary of everything we just talked about. Declaring a variable, here's some examples, where it's always type followed by the variable name. We can assign something to a variable, and again, here are some examples, where we take the variable name equals whatever we're assigning to it. And then finally, at the bottom, we can declare and initialize a variable in the same step, where we have our declaration, followed by an equal sign, followed by the value we're going to give to it. All right. If you had been with us face-to-face, I ask that you go work the type of a variable question from earlier today. Let me pull that up and just kind of show you what the answer to that is, since you're following along at home. So the question, and you can see the results here, was given box-trot controller BTC : what is the type? And the answers were box-trot controller, BTC, or semicolon. And box-trot controller is the type here, and most people got that. All right, then we started talking about primitive data types. So there are two categories of data types in Java. The first are the primitives, and the others are the objects. And we'll talk about the primitives here. Primitives are the fundamental data types for the language, and most of them correspond directly to data that a computer processor can natively process. We have eight primitive types in Java. We're mostly going to focus on the first four here. So ints are whole numbers, and that includes negatives. So -42 is valid, 0 is valid, 1 is valid, etc. It is limited to between about minus 2.1 billion to positive 2.1 billion. And if you've ever heard about the fiasco with the Gangnam Style video that crashed YouTube's views, it had to do with them using an int where they should have used something else that had a much wider range. Double is our floating point type that we use, and it stands for double precision. Terrible name because most people don't understand what double precision means yet. You'll find out later. We'll talk about that in the computer architecture course if you take that. But double is our floating point, so anything like pi or Avogadro's number, 5.0, minus 9.6723, 10 to the minus 7, all these are valid doubles. And it's a very wide range of values there. Boolean is literally just true or false. So any value of, or any variable of type Boolean can only take the value of true or false. It's good for yes/no type questions or yes/no type data. Char stands for characters, and it's any kind of letter, numeral, punctuation, whatever that we see in text, as well as some weird things like certain emoji and other kinds of drawing characters and stuff. So those four are ones we'll use the most. There are also a form of short integer. It's similar to int, except it has even smaller range. There's long, which is like int, but with more range. And then there's byte, which is a very, very small int. It's only between minus 128 and positive 127. Very useful for file and multimedia processing because a byte is the fundamental unit of data storage, really, in practice. And then float is like double. It's a floating point data type, but it doesn't have the range of double. In the past, we used floats a lot because computers weren't as powerful, and it takes less computing power to process a float than it does a double. At this point, our computers are so powerful, we just do double for everything, unless we have a really, really good reason not to. So those are the primitives. These are fundamental types. They come built into the language. We have them ready to use from day one. Now let's talk about object types for a minute, and we'll get more into detail on object types later in the semester. But object types are types built out of other types. So at the very least, an object type must be composed of primitives. The string is a good example of that. The string is an object type. So there's a class string out there, and it contains lots of characters. And by containing lots of characters, we can string them together, hence the name, to create text. So some examples of valid strings are Lewis in double quotes, may the force be with you in double quotes, over 9,000 in double quotes. String constants are always put in double quotes. Those of you who've taken Python, we're allowed to use single quotes. That will not fly here. You can only use double quotes for string constants. You can even do weird things with strings like have emoji in double quotes. These are valid strings in Java, and you can copy paste those straight into your editor because characters are actually Unicode characters. So you can do emoji, you can actually do non-English character sets, lots of typographical symbols, mathematical symbols. It's a very, very large, rich set of characters, and they're adding to it all the time. Okay, statement. Complete program instruction must end with a semicolon. And there you have some examples, most of them things we've seen before. So declaring a variable, int number, assigning to a variable, printing something out using system.out.println. This line, this .firstDoodler.step4, you'll see something like this soon. This is calling a method in Java. All of these are program statements, and your program statement must end with a semicolon. Assignments, we've mostly talked about these already, but here's some more examples. Here we obviously have a Boolean that we're assigning the value of true to. Here we have a double, we're assigning 3.142. Here we have a string, we're assigning a string literal to. All of these have been previously declared. In fact, they were declared, some of them were declared number. No, actually number was a int there. So here it's a, it's a double. Assuming X is an int though, and that Y is also an int, we can do that assignment. We could not assign our string to X because those things are incompatible. All right, let's talk expressions. So in Java, your arithmetic expressions will behave pretty much like you expect them to. A couple things to point out. That is the multiplication symbol, the asterisk. And if you don't know what that is, it's Shift-8 on your keyboard. We can do addition, we can do subtraction, multiplication, we can do division, but that's a special case, and we'll hit that in the next slide. And we can do parentheses and so forth. Order of operation is standard PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. Understanding there are no exponents in Java, so you can ignore that one. Multiplication and division are equivalent, so it doesn't matter. So multiplication is not superior to division. They are equivalent, as are addition and subtraction. And the other thing to note is that the order of operations is left to right. In most cases, it's not a problem, but it can affect your answer depending on what's going on. And then our next slide will illustrate this. So division. If you're doing floating point division, things work the way you want them to. So 5.0 as a double divided by 2.0 as a double will get you 2.5. Easy. 15.0 divided by an integer 4 forces that to be the integer to be a double, still works, and gives you 3.75. So far, so good. Where things get weird is when both numbers are integers. So 10 divided by 2, I mean, if I didn't mention it before, the slash is our division operator, gives us 5. We're good. That makes perfect sense. 10 divided by 3, though, is 3. Integer division has a remainder. So 10 divided by 3 is 3 with a remainder of 1. And we drop the remainder. It is lost forever. We must keep that in mind when we do division with integers. And because of that, our order of operations left to right can cause some problems. So in my sidebar here, I have two expressions that mathematically are equivalent. 10 times 2 divided by 4. 10 times 2 is 20. We divide that by 4, we get 5. That checks out. Your math teacher would be happy with you for that. 10 divided by 4 is 2. Times 2 is 4. So we have the same expression in both places, but because of integer division and because of the order we did things in, we get two different answers. So you must be careful about such things. All right. Now that we've had our expressions, we've talked about variables and assignments, let's do a little bit of a tracing experiment. So when we talk about tracing, we're stepping through code line by line and figuring out what happens. I have some code here. Starting go on each line, we want to figure out what is our value of X, what is our value of Y. Now the answers are on the following slides, but I'm going to type them in here as we go. So first statement, int X equals 64. So the value of X at this point, once I've executed that statement, should be 64. Now what's the value of Y? This is a trick question. Y does not exist at this point. So we're going to write does not exist, or D&E for short. Because it doesn't exist until it's declared. So once it's declared, and we've executed that statement, X does not actually change because that did not affect X in any way. And now the question is, what is the value of Y? And the answer here is we actually don't know. It is currently undefined, assuming it's what we call a local variable. And we'll distinguish between local and instance variables later, but we're assuming it's local. So it's actually undefined at this point. All right, now we have Y equals X divided by 4. Well, X is 64. Divided by 4 gives us 16. X did not change, but now we have a Y of 16. And I hope I'm doing my math right and that I'm not going to make a fool of myself in the next slides because I got it wrong. All right, X equals 5 changes X to 5. Y remains unchanged. On this next one, Y equals X times X. Well, X is 5. 5 times 5 is 25. Oops. And that's what Y becomes. X itself is unchanged because it was not on the left side of the equals. On our next line, Y equals Y plus 1, we look and see what Y is currently. It's 25. We add 1 to it, we get 26. X remains unchanged. And on the last line, X equals X times 3 plus Y. Let's look at the X times 3 first. So X is currently 5. Multiplied by 3 gives us 15. Plus Y, which is 26, gives us 41, I believe. And that gets assigned to X. I'll find out if I did my math right on the next one. And Y remains unchanged. Let's see how I did. Yay, got it all right. And now, because this is going to be used later, I'm going to blank out my answers. There's the complete one. And in this slide, I want you to just visualize how data moved from one statement to another. We initialized X to 64. Later, it was used by this statement, X divided by 4. And only that version of it was used, because in the next statement, X gets changed to 5. So that gets used here and here, as well as down here. So it carried data from this statement to this statement and this statement. And similarly, Y, as it was defined here, moves to that statement. As it was defined here, moves to that statement. One thing we saw there was expression where a variable was on both sides of the assignment operator. Here, if this were algebra class, you would fail because you can't have X equals X plus 2 in algebra. It's mathematically impossible. But this is not algebra, and this is not equality. This is assignment, meaning we take what's on the right and assign it to what's on the left. So what's on the right is X plus 2. So we look at our value of X, 3, add 2 to it, which gives us 5, and assign that to our X. So X is now 5. This is valid in Java, it's not valid in algebra. So we see these things quite a bit, so much so that we have some shorthand expressions for doing things. Probably our most common situation is this. We take a variable and we add 1 to it and store it back. So X equals X plus 1 can be shortened as X plus plus. Similarly, a variable decreasing by 1, like Z equals Z minus 1, can be represented as Z minus minus. Those are valid. As it turns out, every binary operator plus multiplication, division, subtraction can be replaced with a version similar to this. So X equals X plus 5 can be changed to X plus equals 5. Y equals Y times 10 can be replaced by Y times equals 10. And Z equals Z minus 3 can be replaced by Z minus equals 3. Division also works this way, as well as other operations you may see later. All right. Last thing for today is to be aware that we can easily convert numbers to strings. So here I have x is 3, z is a double at 5.3, and I have a string variable named result. I have tried to assign x to result. That won't happen. It's a compilation error, meaning our program is not a true program and will not run at all. Because x is an integer, you can't assign that directly to a string. Now this next one, though, we can. Result colon space is a string, so that could be assigned to result. But we've also not added, but concatenated our integer to the end of it. And so what this does, Java is smart enough to figure out, since x is the number 3, it will change it into a string that looks like 3 and append that string to this string. So what we get is this, stored in result. Similarly, if you want to do a quick and dirty where you only need the number converted to a string without any extraneous text, you can do something like this. Result equals an empty string, 2 double quotes with nothing in between them, and then you concatenate your number onto the end of that. And so now result holds this thing. It's a string that looks like a number. It's not a number, it's a string that looks like a number. That's a very handy way to quickly convert a number to a string. And this works for doubles, works for true and false, for booleans, works for characters. You can append all of those onto a string. All right, well, that is it for today. We have talked about declaring variables, assigning values to them, evaluating expressions, as well as assigning those expressions to variables, as well as a few other things. But this was the bulk of it. If you have questions, always feel free to email me, and I will get back to you as soon as I can. So thank you.